Andromeda is coming. Right now, tonight, above your head, a galaxy of 1 trillion suns is falling toward us at over 250,000 miles per hour, and there is nothing in the universe that can stop it. And yet, here is the part that should terrify you a little, even if you could travel at the speed of light itself, the fastest speed that exists, the speed that nothing in this universe is allowed to exceed, you would still never reach it. Not in your lifetime, not in 1,000 lifetimes, not even close. How is that possible? How can something be racing toward us and simultaneously be unreachable, even at the ultimate speed limit of reality? The answer to that question will force you to abandon almost everything you think you understand about space, time, and distance itself. And to understand it, we need the mind of a man who has spent his entire life making the impossible feel obvious, the physicist Leonard Susskind. Susskind has a peculiar gift. He can take an idea so strange that it breaks your brain on first contact and walk you through it so patiently that by the end you feel almost foolish for not seeing it sooner. He built his career at Stanford doing exactly this, first with quantum mechanics, later with string theory, and later still with the black hole information paradox, one of the strangest arguments in the history of physics. But before we get to black holes, before we get to the edge of the observable universe, we need to start with something deceptively simple, a light bulb, and a galaxy 2.5 million light years away. When you look up at Andromeda on a clear night, what you are seeing is not Andromeda as it is now. It is Andromeda as it was 2.5 million years ago. The light left that galaxy before humans existed, before we had language, before we had fire, and it has been traveling through the vacuum of space this entire time. Arriving in your eye tonight is an ancient message from a moment in cosmic history so distant that our own species had not yet evolved. That alone should give you a strange feeling. But here is where it gets genuinely disturbing. If you built a spaceship capable of reaching the speed of light, a physical impossibility for anything with mass, but let's imagine it anyway, and you launched today toward Andromeda, you would arrive in 2.5 million years measured from Earth's perspective. 2.5 million years. Entire species will rise and vanish on Earth in that time. Continents will shift. The sun will burn through more of its hydrogen. And that's the optimistic scenario. The one where you're allowed to hit the one speed the laws of physics say you can never actually reach. This is where Susskind's teaching becomes essential, because most people assume the barrier here is technological. Build a better engine, gather more fuel, wait for future science, and eventually you'll get there. But Einstein's special relativity, confirmed by a century of experiments, tells us something colder and stranger. The barrier isn't engineering. It's the geometry of reality itself. As an object with mass accelerates closer and closer to light speed, its effective mass, in terms of the energy required to accelerate it further, increases without bound. Susskind often illustrates this with a simple thought experiment. Imagine pushing a shopping cart, easy at first. Now imagine the cart gets heavier every time you push it faster. At ordinary speeds you don't notice. But get close enough to light speed and the cart begins to feel less like it has mass and more like it has infinite mass. You would need infinite energy to close that final gap. Not more energy, not the energy output of a star. Infinite energy. The universe simply does not permit it. Light speed is not a distant record waiting to be broken. It is a wall built into the fabric of the cosmos. So we accept that we cannot go faster than light. Fine. But even accepting that limit, something even more disturbing is lurking underneath the surface of this story. Something that Susskind has spent decades trying to get people to genuinely absorb rather than just nod along to. The universe itself is not standing still while you travel. It is expanding. And not just expanding, but accelerating in that expansion. Here is where the real trap reveals itself. Andromeda, unlike most galaxies, is actually moving toward us due to local gravitational attraction, pulled by the mutual gravity of our local group of galaxies. It's one of the rare cases where cosmic expansion is currently losing to gravity on a local scale. But zoom out just slightly to any galaxy beyond our local group, and the story flips entirely. Because of the expansion of space itself, discovered through the work of Edwin Hubble in the 1920s and refined by decades of subsequent observation. Galaxies beyond a certain distance are retreating from us, and the farther away they are, the faster they retreat. This isn't galaxies flying through space like rockets. Space itself is stretching, carrying galaxies along with it like raisins in rising bread dough. A comparison Susskind himself has used to explain why every raisin sees every other raisin moving away, without any raisin being at a special center. Now here is the part that turns this into a genuine paradox, the part that makes even seasoned physics students stop and stare. There exist galaxies right now, at this very moment, that are receding from us faster than the speed of light. This sounds like it violates Einstein's ultimate speed limit. It does not. And understanding why is one of the most important lessons Susskind has spent his career trying to teach clearly. The speed limit of light speed applies to objects moving through space. It does not apply to the expansion of space itself. Nothing is physically traveling faster than light through its local region of space. But the space between us and that distant galaxy is stretching so rapidly that the total separation grows faster than light could ever cross it. It's the difference between a runner sprinting on a track and the track itself expanding beneath their feet faster than they can run. This single distinction, subtle as it sounds, is the actual reason certain galaxies become permanently unreachable, no matter what speed you achieve. There is a boundary in the universe, invisible, quiet, moving outward in a strange sense of its own, called the cosmological event horizon. Beyond it lie galaxies whose light emitted today will never reach us, not in a billion years, not in a trillion, not ever, because the space between us and them is expanding faster than light can close the distance. And more chillingly, some galaxies we can currently see, whose light is reaching us right now, are already beyond the point where, if we tried to travel toward them today at the speed of light, we could never actually arrive. Their light is still crossing the gap, a final signal from a place already slipping beyond our reach forever. Andromeda, mercifully, is not one of these lost galaxies. It sits close enough, gravitationally bound tightly enough to our local group that it will not be swept away by cosmic expansion. In fact, in roughly 4 billion years, Andromeda and the Milky Way will collide and merge, an event that is not speculative fiction but a well-supported prediction based on precise measurements of Andromeda's trajectory. But for nearly everything else out there, the vast majority of galaxies in the observable universe, the expansion of space is quietly, permanently pulling them out of our reach, 1 light year at a time. And there is no spacecraft, no propulsion system, no future technology that will ever change that outcome. This raises an unsettling question that Susskind has posed in various forms throughout his lectures. If the universe is expanding and accelerating, does that mean the observable universe itself is shrinking, in a sense, cutting us off from more and more of reality as time goes on? The unsettling answer, according to the current standard model of cosmology, the lambda CDM model supported by observations of supernovae, the cosmic microwave background, and large-scale structure surveys, is yes. Billions of years from now, an observer on Earth, or whatever remains of Earth, will look up at the night sky and see only our local group of merged galaxies, surrounded by a vast, dark, empty void. All other galaxies will have receded beyond the cosmological horizon, their light forever unable to reach us. Future astronomers, if they exist, might have no evidence at all that the universe once contained billions of other galaxies. They might reasonably conclude that their small cluster of stars was the entire universe. It's a haunting thought, an entire chapter of cosmic history that could become permanently unknowable, not through ignorance, but through the geometry of an expanding cosmos erasing the evidence. Susskind has spent much of his career grappling with exactly this kind of cosmic horizon, though not always in the context of expanding space. His most famous work concerns a different kind of horizon entirely, the event horizon of a black hole. And the parallel here is not accidental, because in both cases the universe creates a boundary beyond which information and light cannot escape to reach a given observer. Around a black hole, gravity is so strong that not even light can escape once it crosses the event horizon. In an expanding universe, distance itself, stretched by the accelerating expansion of space, can accomplish a strangely similar result, making regions causally disconnected, information exchange forever forbidden, even without gravity's pull. This connection led Susskind, alongside physicists like Gerard Hooft, toward one of the most radical ideas in modern theoretical physics, the holographic principle. The suggestion, still speculative, but taken extremely seriously in theoretical circles, that all the information contained within a volume of space might be encoded on the boundary surrounding that space. Much like a hologram encodes three-dimensional information on a two-dimensional surface. If horizons, whether cosmological or gravitational, define the true boundaries of what information is accessible, then perhaps the universe itself is fundamentally about boundaries and information, not the three-dimensional space we assume is fundamental. It's worth being clear here, the holographic principle remains a theoretical framework, actively researched and debated, not a confirmed fact about our universe. But it has reshaped how physicists think about horizons of every kind, including the quiet, invisible cosmic horizon slowly swallowing our view of the universe. So let's return to Andromeda and to the original question. Andromeda, unlike those doomed distant galaxies, remains within reach, gravitationally, physically someday. 4 billion years from now, its stars will begin to intermingle with our own in a slow, majestic collision that will reshape both galaxies into something new, likely a giant elliptical galaxy. Some astronomers have already nicknamed Milkomeda. Our Sun, if it still exists in some form by then, will likely be flung into a new orbit within this merged galaxy, an event of unimaginable scale happening not through violent impacts between stars, which are so sparsely distributed that direct collisions will be rare, but through gravity slowly rearranging two galaxies worth of stellar material over hundreds of millions of years. But the deeper truth Susskind's work forces us to confront is this. Reachability in this universe is not just about speed. It's about timing, about the specific geometry of expanding space at the specific moment you attempt the journey. Wait too long, and a galaxy that was once within theoretical reach becomes permanently inaccessible, not because you traveled too slowly, but because the space between you and it grew faster than any signal, any ship, any beam of light could ever cross. The universe is not static, waiting patiently for us to develop the technology to explore it. It is actively, continuously erasing parts of itself from our future, sealing off destinations forever, in complete silence, with no warning and no drama, just the quiet mathematics of an accelerating cosmos. And this is perhaps the most profound thing to sit with as you look up at Andromeda tonight, glowing softly in a dark sky. Its ancient light finally arriving after 2.5 million years of travel. Somewhere out there, right now, are galaxies whose light is making its final journey toward us, the last message we will ever receive from them, after which they will vanish beyond our cosmic horizon forever, still existing, still full of stars and possibly life, but permanently beyond the reach of anything we could ever build or become or imagine. We are not just limited by how fast we can travel. We are limited by how fast the universe itself is pulling away from us. And somewhere in that quiet, expanding darkness is a question that even Leonard Susskind, after a lifetime spent staring into black holes and cosmic horizons, has never fully answered. If the universe is constantly hiding more of itself from us, how much of reality have we already lost without ever knowing it was there at all?